Okay, so at this point in time, you should be able to tell me how many valence electrons an element has, and in addition to that, what shell those valence electrons are located in. So if you had an element in the second row that was in group 2A, it would obviously have two valence electrons, and because it's in the second row or second period, those valence electrons are located in the second shell. Now we're going to talk about the attractive forces that undergo when we have electrons and protons. Now we can recall that the negatively charged electrons are going to surround the positively charged nucleus like so. So you'll have your center, which has the nucleus, and it has all the protons and the neutrons. So obviously it's going to be positively charged. And surrounding that nucleus, you're going to have these negatively charged shells. And they're negatively charged because you'll find electrons within these shells. Now, because of the fact that these have opposite charges associated with them, they're obviously going to be attracted to one another. So these electrons in the inner shell and in the valence shell, the outermost one, are going to be attracted to the nucleus because they have opposite charges, similar to how magnets work. Now we're going to talk about some factors that are going to affect this attractive force. So first, let's talk about core electrons. Core electrons are exactly what they sound like. They're electrons that are located in the inner shell, or basically non-valence electrons. And the reason why we're going to pay attention to core electrons is what they do is essentially form a protective barrier or shield the valence electrons from the nucleus. So if we were to say have this random element here, and let's say, for example, that it had two electrons in this core shell and one electron right here in the valence shell. What essentially these core electrons are doing are shielding this valence shell from the force of the nucleus. So essentially they're making it so this valence shell, or this valence electron, is slightly less attracted to the nucleus itself. Now this phenomena is known as shielding. Shielding is exactly what it sounds like. It's basically what occurs when the inner shell electrons block the valence shell from the nucleus. And so when you have an increase in the amount of shielding, you'll decrease the attractive forces that are occurring. So if, let's say, we had another element, instead of having two shells like this one, it had three shells. So we have your nucleus, you have your first shell, your second shell, and lastly your third shell. So the first shell would be filled up very similarly with 2 electrons. The second shell would be filled up with 8 electrons, and we're only going to put 1 valence electron on this random element. Now, as you can tell, this valence electron is being shielded by 2 core ones. Meanwhile, for this element, you still have 1 valence electron. However, this one is being shielded by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 core electrons. And so because this element right here at the bottom is experiencing more shielding, we can essentially say that it is less attracted to that nucleus compared to this top one right here. So again, what we can say is that this one is experiencing less shielding. So that makes it so this valence electron is more attracted to the nucleus. And then for this one, we can say that it's experiencing more shielding. And that increase in shielding lowers attraction to the nucleus. Okay? So now what we're going to do is we're going to take a couple of elements and compare and contrast the number of valence electrons and the number of core electrons between them. So I'm going to take 3 elements that are back to back on the periodic table, those being lithium, beryllium, and boron. If you look at a periodic table, you'll see that these are left to right of each other, back to back. They're all in the second period, and they'll appear from left to right in order. Lithium, you'll see, has 3 electrons in total, with one of them being a valence electron and 2 being core. If you don't know where I got these numbers from, lithium's atomic number is 3, so it has to have 3 protons and 3 electrons. It's in group 1A, so it has to have 1 valence electron. And so if you have 3 electrons total, and one of them is a valence, the other 2 must be core. For beryllium, it's going to be very similar. It has 4 electrons. Because it's in group 2A, it'll have 2 valence electrons. And since you have 4 total electrons and 2 of them are valence electrons, the other 2 must be core. And then lastly, for boron, it has 5 electrons. It's in group 3A, so it has 3 valence electrons, and the other 2 must be core electrons. Now I hope we can see between all 3 of these, you have equal amounts of core electrons or inner shell electrons. What that literally means is the amount of shielding going on from one to the other is not changing at all. And so what that literally means is that going from left to right, shielding is not changing whatsoever. So lithium, beryllium, and boron are all experiencing equal amounts of shielding. So for now, we're just going to assume that the force of attraction stays the same. Now, instead of going left to right on the periodic table, we're going to go top to bottom. So we're going to look at the elements that are below lithium, starting with sodium. Sodium is in the same group as lithium, which just means that it's one below it. So if you look at sodium, you'll see that it has 11 total electrons. It's in group 1A, so it has 1 valence electron. And so if you have 11 electrons total and one of them is a valence, the other 10 must be core electrons. Now we can clearly see that there's been a large change in the number of core electrons. Lithium only has 2 electrons engaging in any shielding, while sodium has 10 electrons engaging in shielding. Because of that, sodium's valence electron is experiencing more shielding and being more protected. So this is less attracted to the nucleus in comparison to lithium. Then we have potassium, which is right below sodium. Potassium has 19 electrons. One of them is a valence electron because it's in group 1A. And so because of that, it has 18 core electrons. Now when looking at potassium compared to sodium, you can see again another jump in the amount of inner shell electrons. Sodium initially had 10 core electrons, potassium has 18. So potassium's valence electrons are experiencing more shielding, which means they are now less attracted to the nucleus. So if you wanted to compare the attractive force between these 3, lithium's valence electrons are experiencing the least amount of shielding, so they are the most attracted to the nucleus. Sodium is experiencing a good amount of shielding, so it's going to be less attracted to that nucleus. And potassium has an even more degree of shielding, so it's going to be even less attracted to that nucleus. Okay? So we can go ahead and add a trend to shielding to see how it changes going from left to right and going from top to bottom. So we already saw going left to right, shielding did not change at all. The number of core electrons stayed the same. However, when we saw going down a group, or top to bottom, shielding increased, or force of attraction decreased. And that was because we were literally adding more core electrons as we were going down the periodic table. Okay, so that does it with shielding. So we're going to go ahead and learn about another term that we'll use to explain the periodic trends, that being nuclear effective charge, which is simply the net positive charge that an atom has. What this is essentially a measure of is essentially a measure of how many protons an element is going to have versus the number of core electrons. And obviously, the more protons that you have, or the higher the nuclear effective charge is, the more attracted valence electrons will be to that nucleus. And so the measure for nuclear effective charge is simply the number of protons minus the number of non-valence electrons, or core electrons. So if we want to bring back our classic example of lithium, beryllium, and boron, we had already stated that lithium has 3 electrons. We're also going to include the fact that it has 3 protons now, with one of them being a valence and the other 2 being core. Now we're going to talk about beryllium, which has 4 electrons, meaning that, this is Be, and we're also going to include the fact that it has 4 protons, not 3, with 2 of them being valence electrons and 2 core. And then lastly with boron, which is to the right of it, has 5 electrons, 5 protons, 3 of the electrons are valence, and 2 of them are core. Now when comparing all of these nuclear effective charges, remember it's simply the number of protons minus the non-valence electrons. So for lithium it's going to be 3 protons minus 2 core electrons, which gives you a nuclear effective charge of +1. For beryllium it's going to be your 4 protons minus your 2 core electrons. So it's going to be, let me abbreviate that. So it's going to be a net nuclear effective charge of +2. And then lastly for borons, you have 5 protons and 2 core. So that'll be a net positive charge of +3. So what we can say about this is that since the number of core electrons is remaining the same while protons are increasing, the nuclear effective charge increases going left to right. So because of that, boron's electrons are more attracted to the nucleus because it has a higher nuclear effective charge compared to beryllium, which has a slightly lower nuclear effective charge, and then compared to lithium, which has an even slightly lower nuclear effective charge. So basically what you can say is that nuclear effective charge is going to increase going left to right. Now if we compare things on the same exact group or the same exact column, you're going to see a slightly different trend. So we're going to go ahead and compare only lithium and sodium. For sodium it has 11 electrons and 11 protons, with one of sodium's electrons being valence and the other 10 being core. If you actually look at the number of protons that sodium has, you'd think that it has a higher nuclear effective charge. However, when you plug it into this formula, you'll see that sodium has 11 protons minus the 10 core electrons to give it a nuclear effective charge of +1. So both lithium and sodium are experiencing equal amounts of force because the number of core electrons are counteracting the number of protons. So going down a group, you can basically say that nuclear effective charge remains constant. And so that does it with these two terms. And there's one more thing that we need to worry ourselves with in terms of attractive forces, and that's simply distance from the nucleus. Now this is a pretty obvious one to figure out. The further away two objects are from each other, the less attracted they're going to be. And the best way to think about it is just comparing two ends of a magnet, a positive end and a negative end. If you start pulling these two away from each other and pretty much increase the distance from each other, you'll see that there's essentially no force pulling the two together. So they become less attracted when they are further away from each other. And the opposite also holds true. So when you bring them closer to one another, you'll see that they become more attracted to each other, like this one right here. So valence electrons that are closer to the nucleus will obviously be more attracted to that nucleus, and valence electrons that are further from the nucleus will obviously become less attracted to that nucleus.